So how do scientists actually use atomic emission spectroscopy in the real world? Because it might sound a little bit silly to just sit around and look at light bulbs through prisms, but this actually has pretty far-reaching consequences, particularly in the field of astronomy. For example, we don't yet have the technology to travel to distant planets and distant stars, but yet we'd like to study those distant planets and different stars so that we can maybe one day figure out where we want to go. And part of the reason where we would want to go to other places is potentially to harvest some raw materials. Let's, for example, take a look at something that we can see from the sun. The only thing that we can really observe about the sun is the light that it's emitting, but it's only emitting light because we have electron excitation happening at that surface of the sun. We see a lot of that light reaching the surface of the Earth. So we can know a little bit more about the composition of the sun based upon the light that we can observe coming out from it. We can look at its emission spectrum. Now, what you're seeing here is actually called a solar absorption spectrum. So this is all of the colors that the light of that actually kind of work to be absorbed by the sun. Now, what we can do is we can compare a solar absorption spectrum to atomic emission spectrum. What that will let us know is what type of materials the sun is actually using during its chemical reaction process. So in the absorption spectrum, that's the one at the top, anytime that the sun is using a chemical, though there will be bands of blackness that will appear in its spectrum, indicating that those particular elements with those particular lines in its spectrum are being used. So really all that scientists need to do are to match up the emission spectrum from the elements that we know to the absorption spectrum, matching up the areas of blackness. And that should tell us a little bit more about the composition of the sun. For example, for the solar absorption spectrum at the top of the screen, we have hydrogen emission spectrum right underneath it. I'm just going to see if any of those lines match up. You can actually see that the two main lines in this hydrogen spectrum actually line up with two black spaces in the absorption spectrum for the sun. What that indicates is that hydrogen is actually present in the sun and is being used during its chemical process. Now, by taking a look at some of the other spectra down further on the page, can you tell, are there any other elements present in the sun? You might want to take pause right now, just hit the pause button and see if you can line up any additional elements. Now that you've had a chance to take a look at the spectrum, you should also notice that the lines in the helium emission spectrum line up perfectly with some additional black line spaces, but they don't explain all of the black line spaces. You also need to put sodium's lines on top of that as well. You'll see those two little lines in that yellow area line up perfectly with the two little line spaces of blackness in the solar spectrum. So at this point, we know it has hydrogen, helium, and sodium. Unfortunately, however, it doesn't look like calcium or mercury would be heavily present inside of the sun. There are no areas of blackness where we see the colored bands in the emission spectrum down below. In order for an element to be present in the sun, those lines do need to match up. Now, I have lots of extra practice ready for you, but I just wanted to make sure that you could see that this is a legitimate technique that we use in everyday life in science.